Okay, so this is for circuit B, the second question. And what you should notice in circuit B is you have this parallel section here, which has got C2 and C3 in it. So I've drawn an equivalent circuit. In my equivalent circuit, C1 has stayed the same, being the 12 microfarads. And I've replaced this parallel section here by a capacitor that I've called CP for C parallel. When you add capacitors in parallel, you just add them up. So the value of that capacitor is going to be 6 microfarads. Remember, micros times 10 to the minus 6. So that would be my equivalent circuit. From this circuit, I can work out the charge stored by each capacitor in this equivalent circuit. So I'm going to do that first. So this will be charge stored by each capacitor in the equivalent circuit. Your formula for charge, you remember, is being Q is equal to V times C. Now, because this would be a series circuit, the charge stored by each capacitor would be the same. So you're really looking at the total charge using the total voltage and the total capacitance. We haven't worked out the total capacitance in this circuit yet. If you have two capacitors in series, then to get the total, go from that to a second equivalent circuit, just having the supply and one capacitor in it, capacitor total, and to get the total capacitance, the 1 over C1 plus 1 over Cp. So you're using the same kind of method you'd use for parallel resistors on series capacitors. And you'll use the 1 over button in your calculator to achieve this. So because they're both measured in microfarads, we're just going to use the 12 and the 6. So I'm going to do 12, 1 over, 6, 1 over equals 1 over my final answer. And that gets me a C total, capacitance total, of 4, and keep my unit the same, 4 microfarads. So now using this 4 microfarads for the total circuit, I can get my Q for the total circuit, which will give me the charge stored in each capacitor in the equivalent circuit. So my V is 12, so Q equals V times C, and my 4 is, C is 4 microfarads, so 4 times 10 to the minus 6. 12 fours is 48 microcoulombs. So that gets you the charge stored by each capacitor in the equivalent circuit. So that'd be by C1 and by Cp. So that really is Q1. Now I've got the charge stored by capacitor Q1. I can get the voltage across Q1 using that charge. That'll be my V1. Transposing this formula, V1 equals Q over C. It'll be Q1 over C1. So 48 times 10 to the minus 6 divided by your 12 microfarads. And that gets you your 4 volts. To get the voltage across the parallel part, Q, which is this Q as well, call it QP if you like. So 48 again. But divided by 6 this time for the value of Cp. And that gets you 8 volts. And that makes sense because 4 and 8 add up to give you 12. and 12 is the supply. So if we know it's 8 here, then going back and looking at our original circuit here, we know the voltage across C2 is going to be 8 volts. The voltage across C3 is going to be 8 volts. So V2 equals V3 equals that 8 volts. And that 8 volts has come from this VP over here, so from this equivalent circuit. So I've taken the voltage across here over to be the voltage across here. They're the same. Then using that V2 and the V3, I can use that to get my Q2 and my Q3. So Q2, V2 times C2, so that's 8 times 2 microfarads. 2 microfarads comes from the capacitor value in the drawing. 8 times 2 is 16. That'll be micro coulombs. Then for my Q3, V3 times C3, 4 micro. (32 microcoulombs). So now you've got the voltage across the first capacitor, the charge stored by the first capacitor, voltage across the second capacitor, charge stored by the second capacitor, voltage across the third, and the charge stored by the third. So that question's finished.